Okay, so in this video I'm going to have a look at rational functions and asymptotes. So this is our rational function here. It's a fraction basically, which is a rational function. And an asymptote is just going to be, well, in fact, if I just draw, if you draw this particular function here, put in values of x and find y and so on, you'll end up with something that looks like this. Now, so we'll have our x and y axis there. I won't put them in. So it's a function that looks like this, and basically what you'll end up with is you'll end up with two lines, a vertical line like this and a horizontal line like this, and you'll find that the graph or the curves here will approach these two lines but never actually meet them. So these lines here will get closer and closer and closer to these red lines, but never actually touch them. And these two lines here are called asymptotes. There's a vertical one and a horizontal one. And what I'm going to do is I'm going to show you how to find the equations of these two lines here. So a vertical line will be of the form x is equal to something, and a horizontal line, as you know, will be y is equal to something. So that's what our equations of our two asymptotes will look like. Now, let's start by just looking at finding the equation of our vertical asymptote first of all. Now, our vertical asymptote will be a point, or will be a line that the curves approach but never reach. So in other words, there is no value of x that will satisfy this function, if you like. Now, what value of x can we put in here that will make this, that won't satisfy this particular function here? There is no value of y, in other words, that will result from putting in a particular value of x here. Well, if we know that this is a fraction here, and we know that it's just the numerator divided by the denominator, and we know that if the denominator was 0, then this wouldn't make any sense at all. You try dividing by 0 on your calculator and you'll get an error. So we know that the denominator here, x plus 1, cannot be 0. So in other words, x plus 1, if we let x plus 1 equal to 0, the denominator equal to 0, and just solve it. So whatever's on the bottom, whatever the denominator is in, let it equal to 0, solve it for x, you'll find that x is equal to minus 1. This here, then, is a value for x. If we put minus 1 in here, for example, we put minus 1 plus 1 will give us 0 on the bottom. So that means this function, that value, we can't find a value for y that will satisfy x is equal to minus 1. So that is very simply our vertical asymptote. The equation of our vertical asymptote is x is equal to minus 1. So that's very straightforward. You just let the denominator equal to 0 and solve for x. That value for x then put into our function here, put into our fraction here, will result in a denominator of 0, which we can't do. We can't find a value for y. Now, in order to find our horizontal asymptote, what we're going to do is find the limit of this function. We're going to find the limit of this function as x goes to infinity. We want x to go out here into infinity in the positive and negative direction. And what would be the limit of this particular function here? So let's just write that out. So we're going to do the limit of 2x minus 1 divided by x plus 1 as x goes out into infinity. So we want x to go out here into infinity, actually in both directions. So if we find the limit of this, how do you find the limit then of this kind of function? We did that in a previous video. If you can't remember, just have a look at that. But basically what you do is you take the highest power of x, in this case it's 1, and you divide above and below by that power of x. So in other words, that would be just the limit of, as x goes to infinity, of 2x over x, which is just 2, minus 1 over x. Remember, you divide each term by the highest power of x, in this case x. So divide this by x, you get 2. Divide this by x, you get 1 over x. Over, divide this by x, you get 1. Divide 1 here by x, and you get 1 over x. Okay, so let's find the limit of this function now. It's the same function, but you know that the limit of 2 is just going to be 2, so that's just going to be 2. The limit of 1 over x, as we know from a previous video, as x gets bigger and bigger and bigger, 1 over x will become 0, if you like. Will approach 0. So that becomes 0. The limit of 1 is always just going to be 1, and the limit of 1 over x is going to be 0. So what we end up with is 2 over 1, which is just 2. So the limit of this function here, as x approaches infinity, is 2. So in other words, that means our horizontal asymptote, or the equation of our horizontal asymptote, is just simply y equal to 2. So now I have the equation of both our vertical and our horizontal asymptotes. Okay, so that's basically how you find the equation of a horizontal and vertical asymptote. What I'm going to do now is I'll just write out some points here. You might be asked to sketch this particular graph here. So what you would do is just put in some values for x and find a value for y. I've done that already. I'm just going to write out a few points that I've calculated already. You should be able to do that anyway. So let me just write out a few points on that particular curve. So I know that I will have 0, minus 1, 1 half, 2, 1, 3, 1 and a quarter, minus 2, 5, minus 3, 3 and a half, minus 4, 3, and minus 5, 2 and 3 quarters. Minus 5, 2 and 3 quarters. Okay, so this is a lot of points that we've got here, and I have my two asymptotes, so I can now sketch this particular curve. So let's see. I have a graph down here somewhere. I put it way down here at the bottom, I think. I might just bring it up a little bit. No, I can plot them here, that's okay. I have my x and y axis here. Now, let's just plot these points. Okay, so I'll plot them in black, I think, yeah. So let's take 0, minus 1. So 0, minus 1 is here. I'm going to have a point here. I got 1 and a half then, so I got 1 and a half here, so it's going to be another point here. 2, 1, it's going to be here. I've got 3, 1 and a quarter, so I've got 3, 1 and a quarter is going to be somewhere around here. I've got minus 2, 5, so minus 2, 5 is going to be here. I've got minus 3, 3 and a half, minus 3, 3 and a half is going to be somewhere here. I have minus 4, 3, minus 4, 3 is here. And you can already see the shape of the curve here that I'm getting. I've got minus 5, 2 and 3 quarters, minus 5, 2 and 3 quarters. So you can see the kind of curve I'm getting here. Now let's just put in our asymptotes as well, just before I actually draw this curve. So let's put in our asymptotes. Let's see, what color will I use here? I'll use green, I think. Let's see, green should work. Okay, so our first one, our vertical asymptote, was x is equal to minus 1. So x is equal to minus 1 is here. So that's going to come down along here like this. Actually, maybe that might be a little bit too light, but you get the idea anyway. It's down along here like this. So we know our curve can't actually reach that particular curve. So let's actually put it in a little bit darker maybe. So yeah, it's the same anyway. You get the idea. It's come down along here like this. You can use a ruler anyway. I'm doing it freehand here. Okay, so our horizontal asymptote we found was y is equal to 2. So y is equal to 2 is here. So you can draw a horizontal asymptote coming along here like this. So we know our curves, this one and this one here, can't actually touch these particular lines here. Okay. Now, let's just draw our curves then. We know what they're generally going to look like. So let's just draw them in here. So it's going to come down here. It's going to get very close to this vertical asymptote. It's going to come down along here, reach these points here, curve around like this, and go off out in that direction. This one here, again, same kind of thing again, get very close to our horizontal asymptote, come around these points here, and down along here like this. So that's the way our curve will look. You'll obviously draw a little bit neater than this. My hands are a little bit shaky here, but you get the idea. So this is our curve here. This is the sketch of our curve. Okay, so let's go back and we'll just do one more thing. I just want to, if you look at this curve here, this pink curve here that we've drawn, you can see that there are actually no turning points here. Normally when we draw, let's say, a cubic curve or a quadratic curve, there's a turning point here, there's a turning point here where the slope is 0. If you drew a tangent here, if you draw tangents here, you can see the slopes of those tangents are 0. So what I'm going to do is prove that there are actually no turning points here either, in either of these two parts of our function. So let's do that. How do we do that? Well, as I said here, if you differentiate this particular function here and let the differential equal to 0, if you differentiate, you get slope, as you know. If you differentiate your function, you get slope. We want the slope to be 0. So if we differentiate this function, let it equal to 0, and show that that couldn't actually be possible, then there are no tangents that we could draw, horizontal tangents that we could draw on this particular curve here. So let's do that. I'll just move way up here again. We'll come back to our original function and just write that out. Our function was, what was it again? Y is equal to 2x minus 1 all over x plus 1. Okay, so I'm going to show that this particular function has no turning points. So to do that, what I'm going to do, to show that a function does have a turning point, or to find the turning point, you differentiate it and let it equal to 0. So I want to find dy dx. Now in order to do that, I can see here that this is a quotient, so we use the quotient rule, which is dy dx is equal to v du dx minus u dv dx, and that's all over v squared. So this is what I'm going to use. So I'm going to say here that this is u on the top and v on the bottom here, so let's do that. Okay, so first thing we want is v actually. V is on the bottom here, so I write down x plus 1. Put it in brackets. Now I want du dx, so I got to differentiate u here. So if I differentiate u, I'll just get 2. Minus, write down u now, that's this part here. U is 2x minus 1, 2x minus 1, and then I want dv dx. V is x plus 1 here, so if I differentiate that, I'll just simply get 1. And that's all over x plus 1 all squared here. Okay, so let's see what happens if I multiply all this out. Well, here I'll get 2x plus 2. Here I'll get minus 2x plus 1. On the bottom then, I'll end up with x plus 1 all squared. Now I'll just move this up a little bit, and you can see here that 2x minus 2x, they'll just cancel out. I'll get 0, and I end up with 2 plus 1, which is 3 over x plus 1 all squared. Okay, so when I differentiate my function, I get 3 divided by x plus 1 all squared. Now, I want to find a turning point. In order to find a turning point, I take my first differential here, which is 3 over x plus 1 squared. I let it equal to 0. Okay, now just look at this here. This is a fraction, 3 divided by something here equal to 0. The only way I can get 0 here is if the top part of a fraction is 0. Remember, the bottom part of a fraction, the denominator cannot be 0. The other way of looking at it is 0 over 1 here. I can cross multiply. 3 times 1 is 3. All of this here times 0 is 0. So in other words, 3 times 1 is 3. 3 must be 0. 3 has to be equal to 0. 3 is not equal to 0. 3 is equal to 3, 3 is a constant, 0 is a constant, they can't be equal to each other, so this is not possible. So therefore there are no turning points on this particular curve. That's it for rational functions and asymptotes, for now anyway.